Aha. We're starting on MIT 5 minutes. Until success. Also, that's good. Have you all been to this room before? No? Nice, okay. I've actually realized once I arrived here that I had been to this room before, but I only realized that once I stood inside of it. Cool. I guess it's 5 minutes in. Should we get started? Cool. It's great to see all of you. This is the first lecture of the course Machine Learning for Inverse Graphics. It's a graduate level seminar, although it's also open to advanced undergrads, where that is mostly up to you, whether you consider yourself that or not. Maybe first I'll introduce myself. My name is Vincent. I'm a professor. I've been at MIT as a professor since 1 year, but I've been at MIT since 3 years. So it could be that some of you have been at MIT for longer than I have. And I'm originally from Germany. So I did my undergrad at the Technical University of Munich. Then I went to Stanford for grad school, and then I came to MIT as a postdoc first, and then as a professor. And I have a research group at MIT, which is called the Scene Representation Group. And basically, much of the stuff we're going to talk about in this course is topics of interest to my research. And so I'm actually really invested in the topics in this course. I'm extremely excited about the stuff. So I hope I can do a good job at explaining why I'm excited about this stuff. And we have so far one TA. That's David. This is David. David is a second year. Oh, actually, why don't you introduce yourself?
Yeah, sure. I am studying my second year. I'm in this group.
Cool. And so that's David. He also knows a lot about the stuff, so he's a great resource. Cool. So we're going to start with some boring stuff because I think some of the questions here that you might have might be answered by that first and foremost. So first of all, in terms of enrollment, last year was the first time I offered this course. Last year it was capped enrollment, only to 40 people. I think we had around 32 in the class. This year is not capped, so everyone who wants to take the course can take the course. If you have a scheduling conflict with this class, all the course materials, including the homeworks, including the lectures, will actually be uploaded online. So some people ask me if they can take the course as a listener. Absolutely, you can also take the course as a listener. All the material is online. The only difference is if you're a listener, we won't grade your homework because David here has limited cycles. But everything else, you can visit the class and you can do everything else just exactly as anyone who's enrolled in the class. Also, if you have any questions, just feel free to raise your hand and I'll try to answer it right then and there. Cool. Second question. If you're not sure if this course is interesting for you, that's the point of today's lecture. So hopefully I can help you decide. Okay, that's not a question. That's just someone waving something down. That's good. So what are the prerequisites of the course? So this is a seminar, right? Though it's, of course, a graded course. So of course, if you really don't know what's going on, that's not great. But the prerequisites of this course are basically you need to be absolutely proficient in Python. So you really need to know how to code in Python because all of the homework assignments will be written in Python and you'll have to code. Secondly, you have to be proficient in NumPy. Ideally, you're also proficient in PyTorch, although we have some introductory stuff that introduces you to PyTorch if you haven't coded in PyTorch yet but have experience in NumPy. Then you should really be familiar with deep learning. So you should know how neural networks work. You should know what backpropagation is. All of the basic deep learning stuff should be in your. You should know about that because we won't go over it again. So we will basically have a few lectures where we just start with talking about neural networks in 3D. And if you don't know about neural networks, it's going to be a tough time. And finally, you should know about linear algebra. So you should know about matrix vector products. You should know what a SVD is. You should know about matrix products and stuff like that. But fundamentally, nothing all that fancy, right? So no advanced math background or something like that. Cool. I should also say that this course is inspired by lots of really cool courses that are taught all over the world. And if you want to really dive deep into some concepts that we might only be able to touch on lightly in this class, then there's these are great resources. So there's lots of great courses you can kind of use to deep dive into any of the topics that we touch upon in class. But also I just want to say these are great, nice people because they allowed me to use some slides from the courses. So cool. So that's the administrative stuff. It's very light. Any questions on that? Fantastic. Good. Then we actually come to the exciting stuff. So the introduction. I usually start my course or any, in fact, talk I give about this topic with an interactive demo because I think it's best for people to understand what this is about by doing a little interactive demo. It's very, very small and not that interesting, but please join me in it. Okay, so I ask you to look around in the space in front of you and maybe next to you, okay? And then I'd like you to close your eyes and I'd like you to grasp for something that you saw. It could be the edge of a table, or it could be like, the edge of a seat in front of you. Ideally, it's not your neighbor. Okay, good. That's it. Done. Great. So that's it. You can open your eyes again. That's the interactive demo. So that was probably not all that impressive, right? You're like, okay, yeah, great. I succeeded at grasping the chair. Okay, but the reason why I bring this up is because I want you to think about for a moment that the thing that you just did is actually something that exceeds the capabilities of computer science to date by far. And what I specifically mean is, even though you actually just have two eyes that constantly capture video, 2D video of the world around you, simplified, it's a little bit more complicated, but basically it's 2D video, your brain actually constantly builds a 3D map of the environment. And that 3D map was what you used to like realize where the thing that you maybe decided to grasp was, right? And the thing that your brain saves or like infers about the world is much more rich than the things you can see. In particular, right, when I look at this chair, what I actually see is just colors. All I can see is colors, and I can infer the rough geometry. But what I actually know about this chair is much, much more than just the things that I can see. For instance, I know that if I poked it, that this thing here would be soft. I even have a belief over what the texture might feel like, right? I know that if I touch the wood is hard. I know that if I try to, I don't know, if I kick the chair, which I won't do, then maybe the chair would break because the wood is like breakable, right? And these are all things that you constantly infer about the world around you, even though you can't actually literally see them. And how do you do that? Well, impressively, you learn all of that not by training on huge labeled data sets, but instead you learn it as a little child, right? You run through the world, you like pick up stuff, you look at stuff, you move your head, you move around, you throw stuff. And that's basically the way you learn about all these properties of the world. And then over time, you learn to infer them from vision. And that is basically what I usually call a scene representation. So the scene representation is the thing that you have in your head that stores information about the world around you. And if you then think about all of these different applications in computer science, which I'm sure many of you actually work on this stuff, I don't know, let's think about robotics for a moment, right? Let's think about grasping or pick-and-place tasks in robotics. Of course, this kind of scene representation inferred from vision is something that is absolutely critical to any robotic task, because you just did it, right? You just executed a grasp with your hand, right? So in robotics, you constantly need a 3D representation, the 3D state of the world, and you want that state to be as rich as possible so that you can make informed decisions and that you can plan. Another example is, of course, computer graphics. Many of the things we will discuss come from computer graphics, but what is computer graphics? I don't know if you play video games or if you watch movies, right? There's lots of computer animated imagery in there. And in computer animated imagery, what is our objective? Our objective is we want to build 3D scenes such that they look photorealistic when you render them, such that you can fool the observer into thinking it's realistic, right? And of course, for that, well, first you need some way of parameterizing that 3D scene, and you need some way of like figuring out how do you parameterize the 3D scene. And ideally, instead of some poor human sitting there and having to build every little 3D thing that you want to render, which costs a lot of money still today, ideally you would want to maybe just reconstruct it from the real world, right? Okay, maybe you want to put a table into your video game. Instead of sitting down and like painstakingly animating a table, or like building a table in a 3D tool like Blender, maybe you would just like to scan it and then pop it into your 3D video game, right? That would be great. And we're getting closer. We're almost there. And the ways we're doing it, we're going to discuss in this course. Then there's things that we haven't actually reached yet and where we don't even have, honestly, like a good way of doing it all together, like physics simulation. So when I say physics simulation, what I'm really thinking is like intuitive physics. So this lady there just took out her laptop out of her bag, right? Sorry for using you as an example, right? But like just this, like actually, I was just observing it. As you were taking out the laptop, you actually did like this complicated flip of like the laptop to put it on your table, right? That's crazy. It's crazy, right? That there's this like this piece of metal that has like significant heft to it, right? And you intuitively know how you have to manipulate it to make sure that, you know, how much torque do you have to apply to make sure that it flips, and then to put it on your table without it breaking or falling down. And that's what we call intuitive physics, right? So like the skill of like anticipating what would happen if you interacted with the world. And this is something, honestly, that in artificial intelligence we have made about zero progress on. And I think, personally, one big reason for that is that right now we don't even have a way of, if you observe a dynamic video, reconstructing the 3D dynamic scene which would then only allow you to reason about the physics that are involved in like how this world is moving. So this is something that we're making significant progress on right now today. In the past 2 years, there has been more progress on this than ever before, and we'll talk about it in this course. But it's still unsolved, literally unsolved. So intuitive physics, big, big open problem, very exciting. And then of course there's like some applications like, I don't know, self-driving cars. If this were to work, this would be a really big deal for self-driving cars because self-driving cars still don't use these things. They are still like very, well, we talked about it in a moment. And then, yeah, robotic vision, some applications, whatever. Okay, and in the past, it's not like people didn't try this before. And in the past, it's not like people, didn't know about the fact that 3D is important. But it is the case that in the past, we always used handcrafted 3D representations. And so for instance, if some of you are familiar with robotics, there's like this notion of SLAM. And who has ever worked with a point cloud before? Show of hands. So like a few people, right? So point clouds is like a classic way in which like computer scientists have parameterized 3D scenes in the past. And in fact, we are still working with point clouds today, but in the past, we always used optimization algorithms or heuristics to build these point clouds and to interact with them. But that's really not what we want to do, right? The lesson of deep learning has been that we really want to use algorithms that are learned from data. We want to use priors that are learned from data to build these kinds of, to build any representation that we interact with. And 3D is not an exception. And in the past, people didn't use deep learning for this. But now we will use deep learning for this. That's the big difference. So we will discuss methods in this class, how we can build 3D representations using tools from differential programming, using tools from deep learning that allow us to build 3D representations as part of bigger models that allow us to learn about all of these things that we just discussed. Okay, that was kind of rough, but like I think, any questions so far? Good, fantastic. Okay, so some more fun, almost philosophy. What even is a scene? I think it is good to think about this for a moment. So let's consider this room that you're sitting in. Because vision is kind of crazy. Okay, let's consider the room that you're sitting in, right? So what makes this room? This room has, again, like a state, it has lots of properties. At every 3D coordinate, basically, this room has some property. So at this 3D coordinate here, the room is like air. Air is mostly transparent, and so on. But at this 3D coordinate here, it's like wood. And how do you observe 3D scenes? Well, you observe 3D scenes because light from these light sources bounces around in the 3D scene. And some subset of these light rays make it into your eye, right? Through your pupil onto your retina. And that's actually the way in which vision happens. The way in which vision happens is that the scene has some state, light bounces around it and collects information about the state of the scene, and finally it ends up in your eye and it dumps some information about that state. But that process is really extremely lossy. You only observe projections of the 3D world, right? At any point in time, you don't, if you close one eye and you really just take a picture of this chair, there's like no way of figuring out how far this chair is away without any learned information about the world, without any experience. So the measurements that we take from the 3D world are extremely impoverished. They really are only like a tiny subset of information that is carried around by the light that is bouncing throughout the scene. And then, of course, you do have other sources of information like touch, but vision is by far the sense that has the highest bandwidth in your brain, and vision is in many ways the most important sense that we have. It carries the most amount of information. And your brain is working really hard all the time to make as much use of that information as possible. Cool. And so now, kind of simplified, what happens in your brain afterwards is that basically we have our 3D scene. Then we have this image formation process, which is the thing that forms images on your retina. And interestingly, this is what we usually study in computer graphics. So in graphics, we build 3D scenes, and then we simulate what they would look like from a camera that is placed in the scene. And then something is happening in your head. At the end of the day, whatever happens ends up with this 3D representation of the scene around you. But how do we get there? So usually we call this, we're going to have this like black box, which we call inference, which basically means the process of going from an image on your retina to the 3D representation of the world around you. We call that process inference. And then this is what gave this course its name. So the course is named Machine Learning for Inverse Graphics. Why is it called inverse graphics? It's called inverse graphics because it's inverting the graphics pipeline, right? Graphics goes from 3D scene to image. We're going to go from image to 3D scene. And then finally, there's like some downstream tasks. And one thing that I hope to convince you of in this course is that literally any task that requires vision, you should be doing on top of 3D representations. Like doing any kind of thing on top of representations that are not 3D aware is fundamentally flawed. This is an opinion, big flag opinion, okay? So like, there are people who would disagree with this, so this is an opinion, well, maybe you will agree. If you don't agree, that's also fine. All the better, we'll have interesting discussions. Okay, and so then a slightly less high-level overview of this course is basically we're going to talk about these three things. In terms of computer science, we're going to talk about ways of actually parameterizing 3D scenes. How can we model a 3D scene in a computer? How can we build neural networks that go from images to 3D scenes? And then we're even talking about some applications. So like, once you have these things, what can you actually do with them? And again, we're going to talk about specific papers, specific algorithms, specific things. Okay, actually, how are we on time? Yeah, I think it's worth talking about this. I was thinking to skip this, but we won't skip it. So this is kind of a funny history. I don't know if you've heard it before. So a brief history of artificial intelligence and deep learning, right? We're going to go through the history of, like, very brief history of deep learning. And there's this particular reason for why we're doing this in this course. It has some fun connections to MIT. So all of you are at MIT, so it's exciting. And secondly, we are going to end up with today, and we're going to talk about what is wrong with AI, or like with computer vision today. Okay, so the thing that started deep learning, arguably, was the invention of the perceptron by these two guys, Warren S. McCulloch, I hope I didn't slaughter that name, and Walter Pitts. And they gave the first mathematical description of a neuron. So it was in 1943, so it was kind of hard to build this in a computer. But they modeled it mathematically. They described, oh, a neuron, like a perceptron is this thing, it has these inputs, and then, you know, it computes an output from these inputs, and then it has an activation function and so on. Okay, so then in 1958, there was this guy, Frank Rosenblatt, and he actually built the first implementation of this thing, and it looked like that, very complicated. Couldn't do that much, but even it's interesting to think about what people back then said about it. They said, like, oh, this is the first device to think as the human brain. And I don't know, would you agree with that statement? So back in 1958, maybe not. It is interesting to see that many of the things we say about today's AI might have a similar level of statement, right? We might also say, oh, this is now something that gets close to the human brain. Maybe or maybe not, I don't know. Okay, and now here comes the MIT story, which I'm excited about. So the MIT story is really fun. So in the 1960s, there was this guy, Marvin Minsky, and Seymour Papert and Gerald Sussman. So these two guys are much older than this guy, which you can tell by that guy being in color, I guess. These two guys were arguably the kind of, I would say, they were some of the first people that formalized the problem of computer vision. Right? They were like, computer vision, and in fact AI. So Marvin Minsky oftentimes is referred to as like one of the founders of the idea of artificial intelligence. And so the funny story here is the Summer Vision Project. Who has heard about the Summer Vision Project before? Oh, so many people, but not everyone. So I'm going to tell the story again because it's so fun. So the Summer Vision Project was this funny thing where Gerald Sussman was a student of Minsky's, I think. And they organized this conference, one of the first conferences on artificial intelligence. And then they were like, okay, computer vision, easy. Computer vision, image in, some 3D representation and some information about the world out, straightforward. So they were like, okay, someone could figure this out in like, I don't know, an afternoon. Gerald, you go. Gerald, connect the camera to a computer and do something with it, report back in 1 year, and by then, we're pretty sure you've got this figured out, right? Okay, so Gerald went off and tried for 1 year and didn't work, right? It really didn't do so hot. And this was the time when people realized, oh, apparently this is hard. And it's interesting because, let me see. The way that, this connects to this, the way that many people thought about vision these days, and this is a discussion that is ongoing until today, the way that many people thought about vision, or like the idea of how you would do vision was basically like primitives-based. So the idea was like, okay, let's say we want to recognize what a car is. Intuitively, you can say, okay, a car is like a box, or it's like a few boxes, and then it has like 4 rounds on it, and then maybe there's like some more lines like this and that, and that's a car, right? And so that was the intuition back then, how people thought you would solve the vision problem. So I think that's what Gerald also tried. So it was basically pattern matching with human-generated patterns. So they would basically make like circles, and then they would try to fit the circles to the image, and then they would make a box, and then, okay. And none of that, literally none of that worked, and it still doesn't work today. And interestingly, they weren't thinking so hard about perceptrons back then, or they were thinking about them, but they weren't excited. And this is kind of where the MIT story gets a little bit sketched, because Marvin and Seymour, they wrote this book about perceptrons in 1969, and they didn't like perceptrons much. And they wrote this particular thing where they said, oh, a perceptron, it can't even solve the XOR problem, which is basically like you train a perceptron to like have the same input-output behavior as a logical Boolean XOR function. And they're like, oh, it can't do it. Actually, they only said that a single layer perceptron can do it. They never claimed that a multi-layer perceptron couldn't do it. And in fact, multi-layer perceptrons can learn this function. But I think it is fair to say that they weren't very excited about perceptrons. And so they didn't really engage with it. And they were, until quite late in their life, I think they weren't big fans of it. And so at MIT, perceptrons didn't really have that much attention at the time. Okay, and then of course, deep learning happened, and there are a few papers that are like the big foundational papers of deep learning, like John Verbos, of course Geoff Hinton, David Rumelhard, Russ, and Yann LeCun. I mean, you know all these people, and that started kind of deep learning, right? And then 2012 happened, and what happened in 2012? The breakthrough in supervised learning. So we got GPUs, a bunch of GPUs. We were like, okay, great. GPUs can accelerate perceptrons. This is the big insight. And now we can just set up a bunch of like supervised tasks, like image classification, and we can crunch numbers, and it works really well. And this was a steep departure of how computer vision had been, like how people had thought about computer vision in the 70s and 80s, right? Which was like this pattern matching. Now, of course, neural networks learn about the patterns themselves. They learn the primitives that they match in the image themselves, as opposed to humans designing the patterns themselves. Okay, good. So now we've almost arrived in today's time. What's the problem with supervised learning? The problem is that labeling is very expensive. If you want to get anything done, you have to collect a bunch of labels. And in fact, there is a more fundamental problem to supervised learning, which is the problem of closed sets. So if you require labels, then of course your neural network can only ever learn what you have fed it as a label, right? It can never learn concepts that aren't present in the labels. And why is that a problem? Here's a funny example. I'm not claiming that this is where self-driving is today. We have, I think, progressed on this, but it's just a very funny example. So stick with me. So this is a Tesla. This is from a few years ago, or like maybe 2 years ago. And this is a horse carriage. So like, let's see. This is the Tesla self-driving thing. Let's see what it does with the horse carriage. That's fine. That's maybe not fine. That's very not fine. Okay. Oh, it's a human. Interesting. A human walking. I don't know. So that doesn't really check out, right? So, and why is this a problem with closed sets? It's exactly the thing, right? There's probably no horse carriage in whatever the Tesla like team did for like classification, right? So if there's no horse carriage, what is it going to do? It's going to explain it with the concepts it knows. And this is really, if you think about it, a gross limitation, right? And why is I'm going to skip this. I want to get to another video first. Why is this a gross limitation? Oh no, now I gave it away. Fine. Okay, look at this frame for a moment, and I'll ask you to look at this frame and then predict what happens next. Unfortunately, you already saw what happened, but it's okay. Just imagine you wouldn't know what happens, and you just look at this frame for a moment, right? And I ask you to look at it and then study it. Okay, and then we're going to predict what happens next. You know, okay, person like, no? One more try. Okay, person faces plate. Oh, disaster strikes. Okay, sad. Okay, so why is closed set? What is the problem here with closed set predictions, right? Like this connects back to our little intuitive experiment that we did, right? But imagine the richness of concepts that has to exist in your mind to like look at this image and then make any prediction at all about what's going to happen, right? There's so many concepts here of like how the world works. There's so many aspects of like the intuitive physics, of vision, of geometry, of all these things. It's just literally impossible to try to do this with supervised learning. We really need to find a way of just learning from the world without human labels. Okay, which brings us to self-supervised learning. Self-supervised learning has recently Okay, so who knows what self-supervised learning means? Like everyone? Yeah, probably everyone. So self-supervised learning, of course, means like learning without labels. Self-supervised learning has had its winning streak. We're getting really close to like even on many of the tasks where we do have human labels, self-supervised models are getting better and better, and oftentimes, sometimes beat models that were trained fully supervised. And here's a few recent successes that I'm also very excited about. Here's a paper called Emerging Properties in Self-Supervised Vision Transformers, short DINO. Some of you might have seen this paper. I don't know if my microphone is in a good position. No. Who knows? This paper is called DINO, and it's quite exciting. So this is a model that has never seen a single human label of anything. It was only trained on images. This is really only trained on images. And this model that was completely trained on images, if you feed it a video, in the first frame, you can click on any pixel that is part of the dog, and then all we're doing is you're plotting the similarity of the pixel that we chose to all of the features that are predicted by the model frame by frame. What that exactly means isn't that important, but notice how this model does a pretty good job at like segmenting out the dog. And it does this without ever having been told what a dog is. It was really only trained on images. This was, in my opinion, quite a big advance in the sense that this is a problem called open set semantic segmentation, which means you don't predefine the sets that you want to do semantic segmentation with up front, but instead you can just hopefully pick any concept. You can just, without the model having ever been told what a bottle is, just by virtue of seeing lots of bottles at training time, the idea would be that you can say, okay, this is a bottle, now find me all the other bottles. So it's like a similarity-based kind of thing. And this has started to work extremely well. This paper came out, I think a few months ago. So maybe a few months ago. This is called Dino V2. And it's this cute little dog running around. And in the bottom right, you can see these feature, like a principal component analysis of the features predicted by the model. The thing that you should notice is that different parts of the dogs have a color that is very consistent across time. So for instance, the model clearly realizes what a dog ear is, right? So the dog ear stays constant throughout the whole video. Again, this is a super hard problem. This is something that has never worked in computer vision forever. And we're it's still not solved, of course, but we're making extreme dramatic advances towards this. And what is this useful for? It's useful for basically everything. So any vision problem needs correspondence. Very cool. Very cool. And here's some more very impressive things, right? This model can find correspondences across instances of objects in very different domains. So here's a bus maybe that is a cartoonish. Here's like a cardboard bus. But if you look at the features are relatively consistent across these things. Okay, that's great. There's kind of a limitation though. These models are still all in 2D. So this model makes predictions about pixels. But if you look at this little toy car, you can imagine what is behind that car, right? It probably has another fourth wheel. But this model has no way of making a prediction about the 3D structure of this object. This model can really only tell you something about the pixels involved. It may know something about the 3D structure of this model, but natively, this model really doesn't account for the fact that this world is a 3D world. Of course, similarly, great advances have been made in generative modeling. And generative modeling for images, I mean, it's just crazy, right? Like, you've all seen this. These are AI-generated images. And it's like just absolutely dramatic, very, very cool stuff. Again, I can tell you that lots of people right now are interested in 3D generative modeling. Why is that? When you build video games or when you build movies, you would be really interested in making 3D models, but however, it turns out that that is really hard. And why is that? It's because we don't have 3D data. We only have images. Just like you as a human don't have ground to 3D information because you only see images. What we have on the internet is just lots of images. We do have some data sets of objects and object classes and so on, but really what we're lacking is there is no good way of doing it. So it's actually, it turns out it's an inverse graphics problem. We want to learn a 3D generative model, but all we have is 2D images and maybe captions for the 2D images. So how can we learn a 3D generative model? And then I already showed you this example. The point of this example, originally what I had in mind, but then I changed my mind, was that I wanted to show you this to, again, highlight the importance of 3D, right? In order to make a prediction about what happens here, it's not enough to just make predictions about pixels. You really have to understand the broader context of the 3D scene. Okay, good. So the role of 3D in computer vision and machine learning and vice versa. any model that interacts with the 3D world needs to make predictions about 3D. It needs a way to make predictions about 3D, and it needs a training time to reason about the 3D world. And it turns out that there's another big problem, which is, I would say, also pretty much unsolved, which is that in vision, 3D gives you lots of properties that you really don't want. So all of the models that we train operate on images, but lots of the concepts that you're interested in, like let's say, for instance, you're interested in classifying this bottle, have annoying little effects in the 3D world. In particular, if this bottle is close to me, the bottle is really big. If the bottle is further away, the model is very small. So for you, that's clearly apparently super intuitive. I don't know how many times someone has moved an object away from you and you changed your mind about what object it is. I guess that does happen with like optical illusions, but other than that, it never happens. But for a model that is operating on images, this is a big problem, as you might know, right? If your model has only ever seen bottles that are this size, and then you ask it to make a prediction about a bottle that is further away, it's going to fail. So the 3D world introduces lots of like weird little challenges that we don't quite know how to deal with yet. Unfortunately, we won't find out how to do that in that course either. But I hope that the tools that we'll learn eventually will help people to solve that problem. So this is actually an unsolved problem. Right now, we just solve it with lots of data. We just say, okay, we're just going to see this bottle at every possible scale. But that doesn't seem like the right answer. Okay, so basically, we need it for everything. Now I'm going to show you lots of pretty pictures to show you what these concepts are actually used for and what the results look like. So Tesla gave a talk, or like a guy from Tesla, Ashok, gave a really cool talk at CVPR, I think 2022, so last year. And they're really interested in the concepts that we're going to discuss in this course because, I mean, just as a little sniding remark, of course they are, because you've seen the little video of before, so that's clearly not acceptable. So they know that as well. So like here's a video of like something that they showed. So this is a 3D scene reconstructed from images that the Tesla fleet has captured from, I think it's, I don't actually know where this is, probably San Francisco if I would have to guess. So for self-driving, this is a big deal. Lots of people thinking about this. Augmented and virtual reality, huge deal. So like companies like Meta, Google invest billions of dollars into the things that we're discussing in this course today, because they want to be able to reconstruct 3D scenes and then re-render them photorealistically such that, or like Apple is a good example. You've all seen the Apple Vision Pro. Many of the coolest applications require you to have an accurate representation of the 3D scene. And the tools that Apple uses for that are some of the tools that we're going to discuss in this course. Actually, I should have replaced that by a Vision Pro video. I'm sure these are much cooler. Other graphics applications. Now, these are actually outputs of papers. So this is a paper called Implicit Differential Rendering. This was a paper that showed how you can reconstruct these very detailed geometries from images. So here's like a human skull reconstructed from images. Here's a paper that was published by NVIDIA just 1 year ago. It's kind of nuts. It seems like, for me, it seems like forever ago, but it's really just 1 year ago. This was one of the, I would say this was one of the first papers that showed how you can use some of these tools at a speed and at a cost that is accessible to consumers. So this is a 3D scene reconstructed from images again, and then you can render novel camera views that is like reconstructed in a few minutes, unlike consumer hardware. So that's pretty cool. Then there's like 3D generative models. So here, these are actually cats that are generated by a little GAN. So this is a GAN. And these are, this is cool. This is a GAN, exactly as we had discussed, that is trained from images, but that generates 3D scenes. And then you can render these scenes from novel views. This is a paper that we recently showed, which showed you how you can edit 3D scenes. So you first can reconstruct a 3D scene, and then you can edit it by like labeling, for instance, flower, or by entering a text query for flower, and then you can edit the 3D scene in an intuitive way. And I think for graphics, I think one of the biggest visions, which many people are excited about these days, I'm sure you've all seen like the Photoshop outpainting and stuff like that, right? So this is an example of like, I think this is literally the Photoshop thing embedded in Adobe. So here, someone is editing this image with the help of like generative AI in 2D. And I don't know if you've ever, I'm not very good with Photoshop. If you take a picture of someone and you want to make them smile, and you are not supported by AI, it's a huge pain, right? Because you have to go in and like work pixels and like touch up pixels is a huge pain. But now with AI, it's really easy. You just click their face, you like make them smile, and then it makes them smile, right? So that's pretty good. Similar here, right? Like I can't paint a tree like that. Maybe you can. I certainly cannot. Similarly, this is a paper that is co-authored by actually one of the people in my research group, but this was not written at my research group. This is a paper from Max Planck Institute in Germany. This is an example of how image editing will look like in the future. And it will literally look like this in the future. I mean, this is a paper. But 10 years from now, I promise you, when you want to edit a picture, no one of you is going to shift pixels around. You're going to go into the picture and you're going to be like, I want this thing to move here. And then you snap your fingers and then the AI is going to do it, right? So it's pretty crazy. And why is this important? Who of you has ever used something to generate something in Blender? Like a few people. Okay, actually, that's a lot of people. I'm very impressed. How much of a pain was it on a scale from 1 to 10? I would give it a solid 10. It's like, yeah, exactly, the worst. It's the worst. Here's an example of someone making this thing. Or maybe this is going to take too long. So like, this is this cool Stargate, Starship Gate, whatever. And like, here's a thing of how they built this thing. And every time I watch this, I just want to lose my mind. Like, this is a crazy amount of effort. Making this gate probably took this person hours of their life, right? And it's very impressive. I have nothing but respect for this insane amount of skill. I could never do this. But like, again, if you look at this, to me, this feels exactly the same way of like editing images did in the past, right? You're like shifting pixels around. Well, in 3D, it's even worse. You shift like these primitives around. No one wants to generate 3D scenes like this. Nobody. How do you want to generate 3D scenes? You want to generate 3D scenes by, like, I don't know, give me a car. And then, okay, now make the car green. And now please make it such that this thing moves over there. And then you want to snap your fingers and then make it so, right? I mean, this is actually a paper. This is actually a GitHub repository that was published some 4 months ago. And you know, this is like very basic still, but you can see it in the future, right? You can look at this and you know how it's going to happen. Like, we can manifest. In 10 years, it's going to be like that. No one's going to edit 3D scenes the way they have edited 3D scenes in the past. Cool. In Vision, actually, I should update the slide because lots has happened in Vision. In Vision, we have basically, well, that's my key motivation. I'm most excited about Vision. But in Vision, lots of cool things have happened. Let me give an example. So if you look at this image, this is actually a paper from our group that was published, isn't even actually published yet. It's just on arXiv. So it's like, it was put on arXiv 2 months ago. So it's like, it's pretty fresh off the press. If you look at this image, it's a fire hydrant. You're going to see lots of these, unfortunately, in our course, because this is unfortunately a very, very hard problem, and the data sets are still kind of limited. But if you look at this image, and I ask you what the back of this fire hydrant might look like, you can imagine a few different solutions of what the back of this fire hydrant might look like. It might look like that. It might look like that. Or it might look like that. Who knows, right? So these are 3 different images. They all look very similar because, of course, it's the same fire hydrant, but the texture changes. You can see that the texture changes, but the geometry is pretty consistent. So in other words, what you do when you look at something like this is that there are some parts of the scene that you are uncertain about, and there are other parts that you're not uncertain about. For instance, you are pretty certain that the back of this fire hydrant also looks like the fire hydrant. So like probably it's round. You probably know that. Could be something weird, you don't know, but it's unlikely. What you don't know about is what is the texture, for instance, right? You have uncertainty about the texture. And so if I asked 5 different people to draw the back of the fire hydrant, they might give me 5 different images of what the texture looks like, right? And this, in fact, is what this model here does. So this model takes single images and then reconstructs a 3D scene. So these 3 3D scenes were reconstructed from the single image, which, again, has, like, this is something that I was really excited about when I started my PhD. This is, like, crazy. This has never happened. Like, this was so far out of reach 10 years ago. You have no idea. Like, the idea that you can take a single image of a real-world scene and reconstruct the 3D scene from that single image was completely out of reach 10 years ago. But nowadays, I mean, it's still not quite there yet. This still mostly works on fire hydrants, which is not the most exciting set of scenes. But it's, again, you see where it's going. Like, this is going to happen. You're going to be able to take a single image of any scene, and you're going to get a photorealistic 3D reconstruction out of it. And you're going to be able to get different 3D reconstructions out of it every time you sample. And this is what this paper was about. So here are the depth maps. So this is the first model that was ever trained on real-world 3D scenes that can sample different 3D reconstructions, different plausible 3D reconstructions of the same 3D scene. Other things that are cool in Vision. So like here's a point cloud, and things that are now possible is that together with language models and together with these kind of foundation models that you might know about, we can now do queries about this point cloud. For instance, here, a comfy place to sit and watch TV. And then using this query, the model can go in and basically say, like, okay, it's this part of the scene or it's this part of the scene. And think about robotics, right? This is a huge deal for robotics. In the future, you want to be able to take a robot and tell him, go pick a glass out of my cupboard. And then you want the robot to do that. Unfortunately, that's like more like 15 years out or like 20 years out. So unfortunately, we're not going to see that anytime soon for many reasons. But this kinds of set of tools that are being developed in this research direction is the thing that will enable that. Okay, another cool thing in Vision. We talked about this, dynamic 3D reconstruction. So here's a swan that is swimming across the lake. Unfortunately, I forgot the acknowledgement here. This is a paper from CMU with, what is it, Jabin? Okay, sorry, I'm going to add the acknowledgement. I forgot about it. But this is a really cool paper that shows you how, given videos, you can then reconstruct the 3D scene such that you can then render it from by changing the viewpoint a little bit. So this takes videos as input and then reconstructs the 3D scene. And remember, in the beginning, I said that's something that doesn't work yet. And it is true, this doesn't really actually work that well yet. So you can even see it on this relatively simple scene. There's still lots of artifacts going on. Yeah, there you can kind of see that the swan doesn't do the right thing. But it's getting within reach. I would say we're going to figure that out in the next 2 years. Maybe one of you will figure it out. Who knows? Here's another cool thing. That's actually not that 3D, but it's very related. So here's a paper where they showed how you can track points. This is from Katerina Fragiadakis' group at CMU. And tracking points across time is really cool. Here's a paper from Andrew, actually, who just joined our research group at MIT, which shows you how to do, again, dynamic 3D reconstruction. I realize now that I told you it doesn't work, and now I'm showing you all of these examples where it does work. But I promise it doesn't actually work yet, in the sense that you can't actually take any video and then reconstruct the 3D scene and the dynamic 3D scene of it. That really does not work right now. Don't want to give you the false impression. But I think what you can tell from all of these papers are extremely impressive, and they do show you that we are at the cusp of figuring this out. Like, this is going to happen. Cool. And then there's lots of robotics papers we're going to discuss. And people in robotics have done crazy stuff, again, that hasn't worked in the past. I could update the slide, but basically there's now for the first time robots that you can, in very constrained settings, you can put a banana in front of them, and they have actually at training time never really picked up a banana before, but then you can tell them, oh, pick up that banana, and it kind of works. So it's pretty cool. And then we're actually going to have a guest lecture of Ellen, who is now faculty at Princeton. She was here at MIT. And people are using some of the tools we're going to discuss in this course also for just fundamental science. So one of the big problems is 3D reconstruction of proteins, the protein structure problem. And there's this thing called cryo-EM, which is basically you put a bunch of proteins, a bunch of them, thousands of proteins, on a really thin slider in a sheet of ice, and then you put it and you shoot electrons at it with a microscope, and then you get terrible pictures out of it with a lot of noise. But then with the tools that we're discussing in this course, and lots of smart other stuff, you can actually reconstruct the 3D structure of that protein, which in the past took 2 years with crystallography, and now it takes not 2 years, a few days. Crazy. Very cool? Cool. Lots of stuff. Anyways, any questions so far? I mean, we didn't actually talk about how any of this works, which is the point of the course, right? But maybe there's questions you have about things that are possible, things that are not possible. I don't know. I actually just want a drinking break. Okay, good. And now we're going to talk about the schedule. It's very tentative because I taught this class for the first time last year, and I had slightly less content back then. Now we're going to add a bunch of content, but I don't actually have all that content yet. So, of course, I have all the content from last year, which already filled one class, but I want to add a bunch of stuff, and that is not yet actually in this tentative schedule. But tentatively, these are the things we're going to talk about. Module 1, this is kind of the kind of math module, or the kind of, this is something we have to talk about because it's actually, in reality, the thing that everyone always has to deal with. And it's very painful, but everyone has to deal with it, and we deal with this all the time. So what we're going to talk about is image formation in multi-view geometry. And what does that mean? It's basically, some of you might have heard about this stuff before, but we're going to study it maybe in a little bit more detail, and you're also going to have a homework assignment about it. Like I give you a pinhole camera. What is the math of the pinhole camera? What is the math of projecting 3D points onto the pinhole camera? What are the different conventions that people use for pinhole cameras? Now, if you move the camera around, what is the math that allows you to like map one camera onto the other? What's the math that allows you to go from a depth map to like a point cloud? All of this stuff. And how many of you have done stuff like that before? Many, but not all. Okay. Camera is like. Okay, good. So we're gonna do that. Yeah, I'm not going to lie. This is the most boring part of the course, I think. I'm actually still excited about it because there's some math in it which is actually quite exciting. Like in particular homogeneous coordinates, which always seem to me in undergrad, they seemed like a trick because they're like, oh, we're just going to append a 1 and then haha. But actually, they're not a trick and they are actually quite cool. Okay. And David made a new homework for that one. It's a very exciting homework. You're going to love it. And it's image formation in multiview geometry. And this is one thing that is new this year, not in this module, which this module really is just like the math. But one part we're going to talk about, which maybe fewer people have heard about, is how these classical algorithms are implemented that take a bunch of images as input, and then they compute the camera poses plus the point cloud from this bunch of images. These algorithms are called structure for motion, or SLAM, simultaneous localization and mapping. And these are algorithms that this community has been working on for 20 years, actually longer. More like 50 years, since the 70s. The first paper on this came out in the 70s. Crazy. And this stuff is really funny and really cool in computer vision because it kind of works, but not quite. And what that means is, like, you can do crazy stuff sometimes. Like, this is a paper from Noah. Today he's at Google and at Cornell Tech. Before that, he was, I forgot where he did his PhD. And he wrote this paper, which was called Building Rome in a Day. He always comes up with the best titles. And the point was, like, we can take images from the internet of, like, thousands of pictures that humans have taken of the Colosseum, for instance, and then we can run this big algorithm to, like, reconstruct where these cameras were and reconstruct the 3D model at the same time, like the point cloud of this Colosseum. And so, and now, basically, this, to a degree, is the basis of many of the things that we still do today. But when I say it doesn't quite work, is that if I now literally were to take a video with my phone of this scene and I would walk around like this, and I would try to run the same algorithm, it would not work. It would break. Or it might work, but it might not. Like, maybe 80% of the time it would work, but 20% of the time it would fail catastrophically. And this is a really weird spot in computer vision because this is the only part in computer vision where we're still not using any deep learning. Like, in fact, many of the algorithms that we're going to discuss that do this like super photorealistic rendering, they all require you that you first compute the poses of the cameras. Like, they first require, if I take a video, you first have to compute where the camera poses were. And that is done with these algorithms still today. And these don't have any machine learning in them. They work exactly, basically, like 30 years ago. And I find that personally very amusing because I can promise you that's not going to stay that way for very long. And the reason why okay, this is a very long arc, but for the first time this year, we're going to discuss a paper that my group published this year, which for the first time goes in the direction to like fix this problem, actually. And we're going to try to solve this with deep learning, and it's going to be amazing. And this will come later in the course, though, because we don't have the tools for that yet. And yeah, so here's some of these existing approaches that we just talked about. So there's like structure for motion in SLAM, and like, well, anyways, you're going to skip this, whatever. This is the paper that we wrote. It's called FlipCam. It's very exciting. Cool. Next. So this is going to be module number 1. And we're going to do this very carefully because we need it. Then module number 2, the exciting stuff starts. So this is where we're going to spend the most of our time. This one will be about 3D representations, rendering, and differentiable rendering. So we're going to talk about how can we model 3D scenes in such a way that like neural networks can interact with them. So like how do you parameterize a 3D scene in PyTorch? Lots of different options for that one. Then we're going to discuss conventional computer graphics ways of doing rendering. And then we're going to discuss how can we make renderers differentiable. So renderers are the algorithms that go from 3D scenes to 2D images. How do we make renderers that are differentiable, so that allow you to backpropagate through that process? And that will be the key, that is the key insight that we figured out in the last 4 years of how we can go from images of 3D scenes to 3D scenes. So this is the basis for all this crazy stuff that has happened over the past 4 years in this field. Cool. And 3D representations are going to be stuff like, okay, we can represent a scene as a mesh, we can represent it as a voxel grid, we can represent it as a point cloud, we can represent it as a neural implicit representation, we can represent it as hybrid implicit or and explicit representations, or sometimes this stuff is called neural fields. This was what much of my PhD was about. Then models of light transport, this is conventional rendering. So how does rendering work in conventional computer graphics? In fact, I'm actually not an expert on this. I mean, I know a lot about it, but I'm definitely not an expert on this. But it's going to be very useful talking about this, and I know enough to do a good job at teaching it, I promise. And then we are finally going to talk about differentiable rendering, which is like something like this. So here you actually have a video of the images of this chair, and then you can snap your fingers, and using differentiable renderers, we can then reconstruct the 3D shape of the chair. Or the thing on the right. And by now, these videos have gotten way more impressive, actually. Like, by now, there's videos where you literally cannot tell that it's not a real video. And we're actually going to also talk about that, in fact. Cool. Then the thing that I'm very excited about is deep learning for 3D reconstruction. So that thing actually doesn't have any machine learning in it per se. People didn't realize that at the time, because in some of these algorithms, there are neural networks. But these neural networks don't do anything that you would consider intelligent or learning, in fact. They're kind of just used as little, well, hard to explain. We're going to explain it later. But there's actually no machine learning in that. But now we're going to talk about machine learning. And this segment is, once we know how, if we have lots of images of a scene, we can reconstruct the 3D scene, then we can think about how can we train neural networks to go from a single image of the scene to the 3D scene. And this is an old example for this that we wrote. This is a paper we wrote 2 years ago. And so here you have a single image of this scene, which is a synthetic scene, and then you can go to a 3D representation of the scene. Note that this is a much harder problem than going from lots of images of a scene to the 3D reconstruction of the scene. We're going to talk about like advanced ways of doing these reconstructions. Like, there's lots of like, there's lots of deep learning tricks that people are doing right now, which we don't understand as well. Like, what is the role of transformers? There's lots of different ways of doing these generalizable 3D scene representations once you have the full deep learning toolbox, and we're going to talk about all of these. And then we're going to talk about geometric deep learning, which is basically the study of exactly what we briefly discussed earlier, where if you have some kind of transformation acting on the data, like for instance, you know that a 3D thing can move back and forth, how can you build a neural network that is, in theory, robust to that? And then we're going to talk about motion. So we're going to talk about how can we actually parameterize dynamic scenes, like stuff like this, and how can we build algorithms that then reconstruct these dynamic scenes from video. And as I said, this doesn't really work yet, but we're almost going to make it. We're almost there, and the tools that we're discussing about will be key to making that work in the next 2 years. We saw this already. We saw this already. We saw this already. And then we're going to have a bunch of applications. We're going to talk about robotics. We're going to have cool guest lectures like Ellen and maybe folks from robotics that are going to talk about how these 3D representations are useful in robotics and how they're using them. And we're just going to talk about applications for these 3D things. Any questions to the schedule? Excellent. What this class will not cover, we won't talk about like advanced topics in computer graphics. So I'm not the one who will tell you about all the tricks of like making path tracing really fast and how path tracing renders photorealistic images. In fact, I couldn't if I wanted to. We're not going to talk that much about mesh processing and computational geometry, which basically like things like remeshing or like things like topology of meshes. We're not going to talk much about that. We're not going to talk too much about like material rendering. So, you know, how can you in computer graphics parameterize a material such that you can render it with the right kind of shiny effects? We're not going to talk much about that. We're not going to talk about the basics of deep learning, and we're not going to talk basically at all about supervised deep learning. All of the algorithms we're talking about are self-supervised. Evaluation. How are the grades computed? We're going to have 4 assignments this year. Last year it was 3 assignments, 4 assignments. 70% total of the total grade. Each assignment is 17.5%. I know that's a really ugly number, but I didn't want to move the percentages around between this and the final project, so this is what it is. It's going to be individual submission, so everyone will submit their own homework. You can, of course, talk about homeworks, but you have to write the code yourself, and you can't copy code from other people. and it's fine to use ChatGPT for it. But David is really smart, so he has built some things that ChatGPT can't help with. So you will actually have to do the stuff yourself. But you're free to use ChatGPT. It's very helpful, I'm sure. Then there's going to be a final project. So there's going to be teams of 1 to 3 people. You're going to write a proposal, which is going to be 5% of the grade. There's going to be a midterm presentation, which is 5% of the grade. I think we're actually not too many people, so I think we can actually have in-person midterm presentations, but we'll have to think about that. Either it's going to be in person or it's going to be a video that you record. And we're going to have a final report and a final presentation. And the final presentation, I haven't decided yet. Either you're going to, again, give a presentation or record a video, or maybe you're going to do a poster session. Might also depend on what you prefer. But I have to think about that. There's not going to be any late days for the report because there's a grading deadline. But there's going to be late days for the homework, namely 5 of them. And after that, it's 25% penalty for every extra late day. And I should say these assignments are not designed to be like super hard. These are designed to be literally useful. Like they're designed to literally help you understand the concepts that you will need if you want to do either research in this area or if you want to use published research in this area. So the objective of this is that once you have done these assignments, you can clone any GitHub repository that is in this general case, in this general area, and you know exactly what's happening in the GitHub repository. Honor code. Don't cheat. Don't copy code from other people. That would be nice. Communication. We're going to have lectures. Oh, this is the wrong room. In this room, we're going to have lectures Tuesdays, Thursdays, 2:30 to 4 p.m. All the slides, all the content will be posted on the course website. The course website is scenerepresentations.com/courses/inverse graphics23. I'm going to post it on Canvas and on Piazza. On Canvas, this is the URL. This is the correct URL. I updated it earlier. On Piazza, this is the URL. I updated it earlier. And this slide will be posted on the website, so you can copy-paste the URL, so you don't have to write it down right now. Yes? Oh, no, it's not the correct URL. Okay, then maybe I was overconfident. I don't know which maybe I edited the wrong slides. That would be a disaster. Anyways, I'm going to edit it before I upload it, I promise. So it's going to be the correct URL. I'm sure you can also find it on Canvas and Piazza. Oh, no. Oh, well, I tried. Don't email us questions. Create private posts to instructors. Post any and all questions. Other people might be able to answer them. And we're going to have office hours. We haven't yet, this is wrong. This was last year's TA's office hours, which was Praful. Praful is amazing, but he's not the TA this year. David is the TA this year. So David is going to have office hours, which are TBD. Is that fair? Yeah. Okay, we're going to decide on the time of David's office hours. We're also going to decide on the time of my office hours, but there's going to be 2 office hours, one for David, one for me. And this is the website, except that there's, this whole site is wrong. I'm just not gonna, and here actually, how topical, disclaimer, this is a new course. This is the second time I'm teaching this course. Of course, there's going to be bugs. Of course, there's going to be everything. I'm a very nice, I like to think that I'm a nice person. So if you tell me, any bug that you tell me, I'll be very happy that you found it. So please let me know if there's something wrong or if I say something wrong. Let me know. I promise I'll be better next year, which you won't profit from, but your future classmates will profit from. Cool. I think that's kind of it. Any questions? Yes. Great. The topics are fundamentally the same. The thing that is different this year is that a bunch of cool papers have come out. A bunch of the concepts have changed. Like literally last year, there's a paper that came out which is called 3D Gaussian splatting. Many of you might have seen it on Twitter or something. It's a cool paper that didn't exist a year ago. So a year ago, everyone was doing something else. So now there's this paper, and that's everyone's going to use that going forward. So all the other concepts remain extremely valuable, but this is a whole new thing. And then another thing that has changed is that I have learned some lessons from giving giving these lectures last time. I still talk too fast, which I realized by looking at the clock, but I promise I'm working on that. There's lots of cool papers that came out, like for instance the camera optimization stuff, which wasn't a thing last year. And yeah, so mostly it's more content. But the basic thing remains the same. I wanted to say one more thing, but I forgot what it was. Right, I think that's it. I think the other key thing is that I got people, I thought last year I got lots of great feedback. People said that they generally found the course extremely useful. The one recurring theme was that I talked too fast. And so I have reduced the content in some of the lectures and split it into 2 lectures to allow me to go more in depth and to force myself to like pace it a little bit better. So that's another thing that has changed. Any other questions? Yes?
I had a question about the make a video.
Yeah.
So you said that basically you show that discussion like not through 10 yet, but
Excuse me, I didn't. Which paper do you mean?
the make a video 4D paper.
Make a video 4D? Oh, you mean the like text query to 4D video? Yeah, I think this is cool. I don't think that model has reliable physics simulation in it. So I don't think you can make that model anything you want it to do. I think it's generally quite limited. The model is far away from like generating kinds of video, far away from the quality of generating images. And in fact, if I would have to make a prediction, then I think that video generation, doing a good job at video generation will probably involve the techniques that we are discussing in this class. I don't think, it could be that just generating frames is enough, but my guess would be that you want to probably generate 3D scenes actually. Cool. That was the first lecture. I hope you find it interesting. I do. And see you hopefully next Tuesday. Hello. Good to see you again. How are you doing?
Doing well.
Yeah?
I see you have some
Yeah. Not much. Just like the objective of that, the objective of this whole module is just really that people know about it.